I'm so sorry that I came only for this for my particular talk. I know how rude this is. And also sorry that I did not provide any title. So here is the title that I suggested. It will be Information Theory, a classical partial view. That is, what, you hear this noise? Yeah. Yes. It depends on my position. Okay. So classical partial view, classical because it will only be classical kind of point of view on entropy and information. Partial because it will be only just one side of the story, but it will be several times in my work, in my research, that I encountered these issues related to Boltzmann, Shannon entropy, and so on. So let's go on, and I will do a kind of review and go a little bit more into just a couple of arguments. And let's recall about the Shannon-Boltzmann entropy. The basics and the history. So first, story starts around 1870 when Boltzmann introduces his statistical interpretation of entropy. Statistical view on entropy, which before that was a thermodynamical concept. And as we know, as we like to see it now, with this idea that the entropy associated with the probability distribution F, which is like the observable configuration, observable, is something like limit as n goes to infinity of 1 over n times the logarithm of the number of configurations which are compatible. Compatible configuration. Okay. And this is the famous Boltzmann formula, S is k log W, which is written on his grave in Vienna. Now, the basic property which is behind, if you want to do it in a computable way, is that when you have f which is f1, etc., fk, so a discrete point of view in which you have only a finite number of states, then S of f is equal to minus sum of fk log fk. And and you can do this either by Stirling or by what people call sometimes method of types, which is saying that mu hat is the maximum likelihood estimate of mu, the law itself, if you have no other information about the law. I mean, the maximum likelihood, a non-parametric estimate of the law, is the empirical measure. And whatever the method you use, you find that there is the error at stage n is like log n divided by n. And there is an explicit error bound and so on, which you can find in this. So conventions. First of all, I will always use H is minus S, so S the entropy, H the information if you want, and I think it is a crime to call H the entropy, even though I used to do it in my first papers, and it's very common practice in partial differential equations, but this leads to big misunderstandings with entropies which are convex, which decrease with time along physical evolution equations and so on. So H, the H function of Boltzmann, more generally, if you have a reference measure nu, and if you apply it to a probability measure mu, will be integral of rho log rho d nu, where rho is equal to d mu divided by d nu. Okay. Sometimes it's called Kullback information also. this quantity makes sense and is used often, even if nu is not a probability measure. If it is a probability measure, then we know that this quantity is non-negative. If it is not a probability measure, it may not be non-negative. It may be ill-defined if nu has tails which are too big or things like this, but there are some simple conditions making sure that this thing is well defined. And also to make the connection with other objects which are familiar in physics and partial differential equations and so on, if we take nu to be exponential minus v of x dx, so reference measure which has the form of exponential of a potential, then 1 over beta h nu of mu is the same as 1 over beta integral of rho log rho plus integral of rho v. If I put here exponential minus beta v, sorry, plus rho v, and this is sometimes often denoted the free energy. So this makes the connection with the combination of entropy and energy and temperature when beta is interpreted as the inverse temperature, which is very common in physical problems. And now, one may argue that there are 4 big results. In this audience, I think they will all be familiar. I will mainly just recall the name. The first that I will quote is the Sanov theorem. It was not the first chronologically, it was in the 50s, but it is the one that captures the idea of Boltzmann in the highest degree of generality, saying that when you draw samples according to a law u, and you draw x1, etc., xn iid, so according to Newton's n, you may recover the energy by looking at something like limit as L goes to infinity, limit as epsilon goes to 0, limit as n goes to infinity of 1 over n log nu to the 10th n of the set of points x1, etc., xn, set of observables such that 1 over n sum of phi L of xi minus integral of phi d mu is bounded above by epsilon, and this for rho L, and this is equal to minus h nu of mu. So this is just an avatar of the Boltzmann formula. S is k log w, put at the right general level of at the right generality. And here we see what it is. We are taking n observations, checking with a set of observable functions. These are these phi 1, etc., phi L, which we think of as the basis of, say, Lipschitz test functions. For each observable, we compare the observed value to the theoretical value for mu. If the error is always less than epsilon, we decide it to be admissible. Then we look at the volume of this admissible configuration, take the logarithm, divide by n, let the number of observations go to infinity first, then the accuracy of the measurement go to 0, then the limit of the number of measurements will go to infinity. If you change the order of limits in any other way, you obtain something which is trivial. So it has to be this order and no one else. And the way to say it is that the empirical measure mu hat n satisfies the principle of large deviation principle of rate function h nu. When the data are sampled according to nu. And so it tells if I have a sample and I want to reconstruct the law, the probability that I am missing, and my impression is that it will be some measure mu which is not the right measure mu, this probability is something like exponential minus h nu, n h nu of mu. So a probability which goes down exponentially fast as n goes to infinity, the probability to make a big mistake on the law. So this is the Sanov theorem. The second is the Boltzmann theorem, the Boltzmann's eighth theorem. This was the start of all the story, 1872, beautiful pieces of physics and of mathematics. And it tells us that dH dt is non-positive where h is what we defined, and the evolution is along the Boltzmann equation. So dTf plus v grad xf equals q of ff, and this is a nasty Boltzmann collision operator, which is integral on R3, integral on S2. Let's write it in general dimensions. It will be the same. Of f of v prime star, minus f of v star, multiplied by v of v minus v star sigma, with integrated against dv star d sigma. And here is the usual Boltzmann picture. If I draw in velocity space the velocities v and v star of two particles which are colliding with respective velocities like this, then the outgoing velocities will be something like this: v prime star after the shock. Sigma is a unit vector which is chosen on the sphere according to a certain distribution depending on the relative velocity. There is a collision angle theta. Which angle is chosen is not known a priori. There will be a statistical distribution of angles, and it's defined on the physical regime. For instance, the most famous case is b of v minus v star sigma equals constant times v minus v star, the so-called hard spheres model, which models billiard balls. But if you take Coulomb interaction, it's a different one. If you take inverse power forces, it will be a different one, etc. All of this was understood by Boltzmann and Maxwell, and we have to see it like some kind of mixing process. You see, when v and v star are taken together, the outgoing velocities are combination of v prime and v prime star. A good analogy for people who are information theoretically oriented would be when you replace 2xy by x plus y divided by square root of 2, x minus y divided by square root of 2, you know. At the level of the laws, it corresponds to some convolution here and some convolution there. It has a flavor of what happens here, in which these things are a bit convolution-like. And indeed, there is an analogy, there is a parallel between the Boltzmann collision operator and convolution operators, which some people have worked on. Anyway, this fundamental thing expresses the fact that the entropy is increasing under collisions, and it was the first important use of the entropy, and it became the foundation of statistical physics for many decades. So this is the second theorem. Third theorem that I will mention is the Shannon's inequality. Let's write it in the form that n of x plus y is bounded below by n of x plus n of y, where n of x is exponential 2 over n times s, 2 over d times s, divided by 2 pi e, the entropy power functional of Shannon. Showing that when you look at the convolution, here I am identifying the entropy of random variable to the entropy of the law of random variable. Here x and y are supposed to be independent, and so x plus y at the level of the laws is like a convolution. So it expresses the fact that under a mixture process like convolution, the entropy has a tendency to go up. There is a parallel between these two statements. Each of them expresses the ability of entropy to increase under a certain mixing process, but it would take, it was only at around the 80s that the parallel was made explicit, and even later that some proofs arrived that really tried to import from one to the other. And the fourth big result, let's say, is the Shannon's compression theorem, which I will not evoke here. So here we have these four big results, and that somehow lay the scene for the sequel. As we know, Shannon rediscovered the Boltzmann entropy functional by completely different reasoning. But for some deep reasons, it had to be the same. based on the interpretation of quantity of information. This is first act. Second act in information theory from functional point of view, one may argue, was the introduction of the Fisher information. Fisher's information. So this arises around 1922 as part of the theory of maximum likelihood estimates as developed by Fisher. And the problem was about estimating the efficiency of estimators. Like some of them may be more efficient than others in capturing the right value that we want to observe. And a definition is, so one possible definition is if you have a reference measure, let's call I nu of mu is the integral of grad f square divided by f d nu, where f is equal to d mu over d nu. Well, it should be a rho to be consistent with my previous notation. Notice, when we have this, it means there is a gradient here, so there has to be a metric structure, geometric structure underlying. It might be Rn, Euclidean Rn, or something else. But it is also used like this, for instance, in a non-Euclidean geometric context. There are several ways to rewrite this, of course. It can be integral of grad log rho square rho d nu. It may also be written as integral of minus Laplace log rho times rho d nu, or if you want, integral of minus Laplace log rho d mu. And this actually is the form that Fisher started from. Let me also notice that the original Fisher definition is when you have a parameter theta, and then you have rho theta, a family of densities, and then the definition would be integral d rho divided by d theta square divided by rho d nu. So here we understand very well theta as the parameter that we want to estimate. Here in this, it is as if, so both coincide, if rho theta of x is equal to rho of x minus theta in Rn. So when we write this, is it as if we have a family that, so that we know the shape of the distribution, but we don't know where it is centered. And estimating this center corresponds to this. So this is intrinsic quantity associated with a certain profile, and it says up to translation how difficult it is to reconstruct this missing parameter. Okay. And the other remark is that there is also a matrix form. There is also a matrix form in which it will be something like integral dy rho dj rho divided by rho d nu. And this is a matrix with indices ij. So when I am writing here this, it's like the trace of this matrix. And the matrix, the Fisher information matrix, by the way, is also used in non-parametric statistics to construct priors which are invariant under certain transforms with the procedure of volume in Riemannian geometry. So this was the definition, and why was Fisher interested in this, and which are the bases of the theory? Let's say that there are three big results related initially to the Fisher information. 3 big results. The first one, which is very simple, is the Kramer-Rao bound from the 40s, which says that variance of theta hat is bounded below by n divided by I of theta. This is using this general definition of the Fisher information. If this is an unbiased estimator of theta, so that the Fisher information gives you information about the minimal variance of an estimator that will try to capture your parameter. And if the Fisher information is very high, this may be good for the estimate. If the Fisher information is very low, whatever you do, your estimate will have a variance which is not so good. The second is about the efficiency of the maximum likelihood estimate, and saying that if you look at square root of n times theta hat maximum likelihood estimates minus theta, here this is the number of independent experiments, and this converges to a normal distribution with mean 0 and matrix which is the inverse of the Fisher information matrix, so that the maximum likelihood estimate asymptotically achieves the best bound that one can imagine and is asymptotically unbiased, which for Fisher was one of the strong motivations for advocating the use of the maximum likelihood estimate. The third big result which I will mention, which is not as famous as the first two ones, but which at logical level is the analog of the Sanoff theorem, is the Donsker-Varadhan principle of large deviation, maybe from the 80s. And it says something like, you remember, Sanoff was about large deviation principle for the empirical measure. So Sanoff, I put it in some place here, was about probability that 1 over n sum delta xi is approximately equal to mu, and this was something like exponential minus n h nu, something like that. This was Sanoff. Now Donsker-Varadhan is the same thing, but if we try to estimate the measure not through independent sampling like this, but through the stochastic process for 1 over t integral from 0 to t delta xs ds. And here this is a stochastic process associated with the, let's write it like this, dt rho equals L rho, the generator with reference measure mu. It will be the heat equation if the measure is uniform. It will be a Fokker-Planck equation if the measure has some potential, and so on. And it says that the large deviation principle for this rate function is the Fisher information with respect to nu. So it will say something like, so this will be Donsker-Varadhan, probability of 1 over t integral delta xs ds is approximately equal to mu, is something like exponential minus s I mu divided by constant. These are the, let's say also, these are the cornerstones of Fisher information analysis. And as we know, there is a big relation between H and I. Is that when we look at the time derivative along the heat equation, or this process here, let's write it dt rho equals L rho of the H function, it is minus the I function. So looking at the infinitesimal variation of the entropy with respect to the diffusion process will give us the Fisher information. Okay, now a remarkable thing about these functionals is that they can be combined in many ways in a number of inequalities, functional inequalities which can be used as toolbox in many problems. And let me distinguish four types of information theoretical inequalities, and in various problems I encountered all of them. So the first functional inequality, first type of functional inequality that I will insist on is the evolution under some kind of mixture. So three inequalities. And there are many papers about functional type information inequalities. Let me say that the first time will be the evolution under some kind of mixture. Okay. Archetype would be the Shannon-Stam inequality. Here it's for the basic quantity h, no reference measure, or Lebesgue reference measure. H of square root 1 minus lambda x plus square root lambda y is bounded above by 1 minus lambda h of x plus lambda h of y. Here when I write h of x is h of log of x, as usual, and x, y are always assumed to be independent. This inequality is actually equivalent to the Shannon entropy power inequality through some rescaling. But in this way, it appears even much more like some kind of convolution, even if there are some convexity inequality, even if there are these square roots, which are the only possible form compatible with the preservation of variance, with the additivity of the variances. And similarly, there are the Blackman-Stam inequalities, which are exactly the same with the I functional instead of the H functional. Again, here this is with respect to Lebesgue measure. So one type of inequalities will be like this, and it's a more general principle. So one thing which I proved in some paper from the end of the 90s, some analog for the Boltzmann equation, for the Boltzmann collision kernel. So let's write Q plus of fg is the double integral of f prime star, the same as I wrote there, b of cos theta dv star d sigma, so the same operator as I wrote here, but in the restricted condition that the collision kernel B only depends on the cosine of the deviation angle, not on the modulus of the velocity. This is a so-called Maxwellian assumption, which goes back to Maxwell himself, and in physical world would correspond to particles such that the interaction between them is like the 1 over the distance to the power 5. Such particles are used in modeling in certain areas of plasma physics, for instance. But for Maxwell, it was just a mathematical trick to simplify some of the things. And we assume that integral of b of cos theta d sigma is equal to 1. So when we have this condition, sorry that I put f and f, in fact it should be f and g. And when we have this condition, we have h of q plus of fg is bounded above by half of h of f plus h of g. And similarly, I of q plus of fg is bounded above by half of I of f plus I of g, Fisher information. So expressing this bridge parallel between the theory here where we have rescaled convolution and here where we have Boltzmann type operators. As a consequence, for this kind for this kind of B, for such B, not only is the Boltzmann H functional always going down with time, but also the Fisher information is going down with time. People in numerical simulation say that in practice you always observe this thing. For Boltzmann equation in the for the equation which is so-called spatially homogeneous, just dTF equals Q of FF. But we know how to prove it only in the case of Maxwellian molecules, and we're not sure whether it's true for more general cases. So this is the first type of information type inequalities in which it's the mixture that plays a role. Second type is, of course, along the equation mixture or along diffusion equations. Well, diffusion equations establish some kind of mixture, so it's related. For instance, there is the concavity of power entropy, d square dt square n of st mu, where this is the heat, is non-negative, non-positive a long time. What do we have here? Let's say that this inequality actually is more general and extends to all manifolds with Ricci curvature bounded below by 0. The interplay between Ricci curvature and information theory was one of the big discoveries in, at the interface of analysis and probability and geometry around 15 years ago, and I will come more to this. But for instance, this kind of identity, which when you see the initial proof seems to be strongly related to Rn, actually works as soon as you have non-negative curvature. The second type of inequality that I will insist on are dominations of an information by another, or bounds between informations. Okay. The most famous, very clearly, is the logarithmic Sobolev inequality. If we write gamma to be the usual Gaussian, exponential minus x squared divided by 2 pi to the d over 2 on Rd, then h gamma is always bounded by half of I gamma. And it's powerful, very famous inequality because gamma is essentially an infinite dimensional object. You may take the dimension to be whatever you want. It will not change anything. No constant here will depend on the dimension. And here you have something with gradients, here something with nonlinearity. So it plays the role of Sobolev inequalities for large dimensions or infinite dimensions. This, at the end of the 80s, was generalized, again under geometric assumption. If you are considering a measure nu to be exponential minus v times the volume measure on some Riemannian manifold, and if the Ricci curvature of your measure plus the Hessian of the potential v is bounded below by lambda, strictly positive, then you have that for any mu, h nu of mu is bounded above by I nu of mu divided by 2 lambda. Consequences of such inequalities are enormous. They are used to do concentration theory. They are used to study the rates of convergence to equilibrium for diffusion processes. they are used to do all kinds of analysis. And if you remember the large deviation interpretations, they also have some interesting interpretation in terms of sampling. When such an inequality holds, it says that somehow estimating a measure by the stochastic process is never worse than estimating it by independent samples. Because the probability of making an error through the evolution, through the process, will be decaying exponentially fast with this coefficient, and the other one will be decaying fast with that coefficient, which is smaller. Sometimes these inequalities will be other well-known inequalities in disguise. And it's very striking, the number of functional inequalities and inequalities from functional analysis, which you can recast as information theoretical inequalities, possibly with variance of the Fisher information or the Shannon entropy. So much less known example. Let's work in Rn. And let's take P between 1 and n. And then for any probability density rho on Rn, we have that integral of rho, grad rho minus 1 over n to the power p is bounded below by some constant p, which is strictly positive. Okay. Here you see it's a variant of the Fisher information, replaces the exponent 2 by p, replacing the log by a fractional power of rho. And by the way, as n goes to infinity, this should correspond to something like Fisher information. But this inequality is nothing else than the Sobolev inequality in disguise, which says that if you take a function u in LP, of a function u whose gradient is in LP, in Rn, then this bounds the higher power of u. P star will be equal to np divided by n minus p. So these are inequalities which are of extremely frequent use in functional analysis and partial differential equations, and there is a theoretical interpretation of this. I wrote paper together with Cordero and Cordero, Nazaré, and myself, in which actually we used these reinterpretations and tools from optimal coupling theory to give very short proofs of Sobolev inequalities with optimal constants. The third kind of inequality which I will mention is domination of a distance by an information. Most famous is the so-called Talagrand inequality, which says that if you take the Gaussian measure, again, and any other probability measure, mu, so for any mu probability measure on Rn, the Wasserstein distance of order 2 between mu and gamma is bounded above by square root times 2 times the square root of 2 times h nu of mu. This is gamma. Where Wasserstein distance of mu and nu is the square root of the infimum of the expected value between x and y square, with x distributed according to mu and y distributed according to nu. This distance of optimal coupling is also very well known in statistics. And when it's written like this, you see, it's very easy to give an interpretation. Because here we are minimizing the expectation of the square norm of x minus y. and because the expected value of x squared is given through the law of mu, and the expected value of y squared is given through the law of mu, this actually is like maximizing the correlation between x and y. So in this distance, it's like you are given two signals, and you look for the maximal correlation between them. You realize these signals jointly with as much correlation as you can, and you take the expectation of the L2 distance between the two signals. Natural distance. And then we have this beautiful inequality which bounds this distance by the entropy, by the information. It was also generalized to much more general context. And for instance, at the end of the 90s, together with Felix Otto, we proved that whenever the reference measure nu satisfies a logarithmic Sobolev inequality, which means for any mu, h nu of mu is bounded above by I nu of mu divided by 2 lambda, then it satisfies also Talagrand inequality, which will be for any mu, Wasserstein distance between mu and nu is bounded above by square root of 2h nu of mu divided by lambda. So from an inequality between informations, you can deduce an inequality between distance and information. And yes?
Question, in the Wasserstein distance, you require x or y to be bounded somehow?
No, just this. They should have second moments. So expectation x y squared should be finite. That's all you require. There is a range of powers. You can put any power between 1 and infinity. All the interesting powers are between 1 and 2, actually. And I would even say the interesting powers are the Wasserstein 1, which will be infimum of expected value distance xy, and the Wasserstein 2, which is infimum square root expected distance xy square. Many applications use exponent 1, many applications use exponent 2, and some applications work only with exponent 1 and some others with only exponent 2. So you need to know both. I will come back to this in a short while. Let me also say that there is, in fact, it has to be thought of, and this was major understanding from 15 years ago, Wasserstein and H and I form a kind of triplet with some properties. And we have to think of this as distance, this is the function, and this is the gradient, or square gradient to be, would rather be. So you know, you change the distance, it changes the gradient, and that's really how it should be thought of. With respect to this distance, the gradient function of h is like the square root of I. And after I have said this, you will understand why the fourth category of inequalities that I will write is interpolation inequalities between distance and information. And the main one is the one I proved also with Felix Otto around 2000, that if if nu has non-negative curvature, okay, what does it mean? Well, if nu is exponential minus v dx, volume minus v volume dx, then it means that Ricci plus the Hessian of v is bounded below by 0. If it has this, then for any mu, h nu of mu is bounded above by w2 of mu nu square root of I nu of mu. A very neat inequality which allows you to bound the Shannon information by a combination of the Wasserstein distance and the Fisher information. Okay. One could go on like this with many terminal inequalities, but then you ask, what do you do with this? Which are the applications that would be used to solve some problems? Let me list some of the applications and what kind of problems such inequalities were put to. Not being exhaustive, but a good sample. Some applications of entropy and information inequalities, let's say, beyond their original use. So first, I mentioned it even though it's not closely related to the rest. In the end of the 50s, there was the famous Nash proof of regularity for non-smooth diffusions was using entropy in a very unusual way, because entropy is about statistics, regularity is about variations. So this was a big shock. Interestingly, Nash had heard about the entropy through Carlson, who himself had worked with, had learned it from Kahneman, who was one of the early experts on the mathematical theory of Boltzmann equation. So it really was from the Boltzmann world that he got the idea. The team of Varadan and others used entropy for hydrodynamic limits. And it's a field in, for instance, logarithmic Sobolev inequalities, interpolation inequalities, and so on. All these can be considered as toolbox in this. The kind of problems is like you give yourself a microscopic interaction on particle system, like diffusion, nonlinear diffusion process. Nonlinear in the sense that the potential of interaction will be nonlinear. And then you rescale, look at things from a distance, and ask which is the macroscopic evolution which is obtained. Typically, a macroscopic nonlinear diffusion equation in the kind of systems that they look at. And because it's naturally infinite dimension, it's important to have analytic tools which work in infinite dimension. Voiculescu, it's one of the most amazing applications in the stuff, defined an entropy for families of operators in certain von Neumann algebras. These are the so-called factors of type 2-1. And he introduced this thing, which was a new entropy, by copying the Sanov theorem, and so the intuition of Boltzmann. And it allowed to solve some problems which are untractable before in operator theory. But also, it will be time. Boltzmann, in the theory of Boltzmann equation, it was important in the first nonlinear estimates of convergence to equilibrium. So again, it's a story that I was part of, and in particular through this so-called conjecture of Cierciniani. So this, I think, was quite interesting twist on information theoretic inequalities, and it's a theorem that is completely, it says just that one functional is larger than another one. So It was, I worked on this with Toscani in 1998, and then I was back to it in 2003. It says that if B of V minus V star sigma is bounded below by 1 plus V minus V star square in the Boltzmann collision operator, then the entropy production of Boltzmann, you know, it's the time derivative. It has some kind of ugly shape with these notation from before. We have this. Then we have a logarithmic thing. Then we have B, dV, dV star, d sigma. Okay. And this is bounded by some constant times the h of f minus h of the Gaussian. And the constant only depends on h. And the integral of f d square, integral of f, and the dimension. So an inequality that tells you that the amount of entropy that you produce is always bounded below by a multiple of the difference between the entropy and the entropy of the limit, the Gaussian, which is the limit that you want to achieve. Okay, this was just one first step in getting some explicit convergence estimates in that Boltzmann problem. Then it was a much longer story. And in the way, in the proof of this, the Blackman's time inequality was used. The relation between the Fisher information and the entropy were used also. And a key thing in the procedure was to time differentiate this thing along a Fokker-Planck equation, which doesn't make real physical sense, but did work. And the last application I will mention, last one, was build a theory of non-smooth Ricci curvature. So this also I was strongly involved in, and even wrote a 1,000-page book on this topic mostly. And it was a story about how do we say that geometry is non-negatively curved. How to say that curvature is non-negative. Okay. People will tell you, and they have worked on this, that the so-called curvature dimension 0 infinity criterion is the one I was giving. Ricci plus a correction which depends on the weight if you are working with a measure which is not the volume. This is a definition of non-negative curvature, and there are many inequalities about this. And Ricci, of course, requires some smoothness to define its curvature operator. It depends on second derivatives of the metric. And for quite some time, there was the problem of how you define for non-smooth space, for instance, a metric space, the Ricci curvature. And the answer is the following. And now it's clear that this is the right answer. If you take a metric space, xd, with a measure mu, reference measure, think of it like the volume, and assume it is a geodesic space, so that there are geodesics in there, but zero assumption on the regularity on the space. Then say that the Ricci curvature is non-negative, so to speak, if, by definition, whenever mu0 and mu1 are two probability measures on X, there is a geodesic mu t, for t going from 1 to t, in the space of probability measures on X, equipped with the distance W2, along which h nu of mu t is bounded above by 1 minus t, h nu of mu0 plus t h nu of mu1. So you define the curvature to be non-negative by a property of concavity of the information, of the Shannon information of the measure along the geodesic in the space of probability measures. This definition does not need any smoothness, but with this definition you can prove many theorems which are characteristics of a non-negative curvature. And it was also in the same order of ideas the h nu functional is used to define the heat equation. We all know and love the heat equation, but it requires a Laplace operator. What do you do if your space is not smooth and you want to have a Laplace operator? Answer, by definition, the heat equation will be the W2 gradient flow of h nu. So it will be, you know, I told you about this idea which was already in Shannon that the mixture will increase the entropy, will decrease the information so that H will have a tendency to go down under the heat equation and so on. Here we take it as definition, so to speak. We define the heat equation as the equation which makes the information go down as fast as possible in the geometry of W2. And this one is due to Ambrosio Gili Savare. And now it's clear that it's also the right procedure to define heat equation in any kind of geodesic space. So as you see, it's all connected. These inequalities they come at some center point between problems from physics, problems from analysis, problems from geometry. This here allowed to solve some problems in geometry, which were problems of honest geometry that seem to have nothing to do with information. To quote just an example, take a family of geometries which converge to some limit geometry in a very weak sense, just convergence of distances and volumes. If all the geometries in the sequence are non-negatively curved, how do you prove that the limit is non-negatively curved? Answer, going through this interpretation of information which is convex along the ways and so on. And so it was. This information has somehow invaded areas of mathematics much larger than what it was used to. One of the most mysterious developments was a construction by Karl Theodor Sturm of a measure which can be written in this form, so to speak, and which is defined canonically in any geometry, and which looks as some kind of some paradoxical properties that are reminiscent of the Wiener measure. Nobody really knows how to use it, but it's beautiful canonical measure giving the biggest weight to the measures with high entropy, and is strongly related to this or that construction. Okay, and with this I finish. They are shy about the first question. Here I see some young man with a big question. Yes. Yes.
What can you say? You have mixing paths with variance preserving paths, right? Suppose you don't have variance preserving path. Are there other techniques where you don't have variance preserving path you can use to show some monotonicity or going in some direction? Because I mean, are there examples of such kind of
Examples where mixing?
You don't do a variance preserving path like a diffusion like root lambda or 1 minus lambda, because that preserves variance, right? It preserves second moment.
Oh, yes, of course.
So I want a path which I want to show monotonicity, but using a path where I don't want to preserve variance, but I don't have control over one.
You mean something that will increase but not to the maximum, will be stuck?
Yes, somewhere. So are there techniques?
Of course, there are other things. So for instance, let's go back to Boltzmann equation. Take Boltzmann equation in a box, then it's a main result that it will converge to the maximum entropy which is available in the box. But if your box has some this is for a box which is, say, a square or whatever. But if your box has an axis of symmetry, then there is an extra symmetry in the system and preservation of some angular momentum. And you do not converge to an equilibrium in the physical sense. You converge to a stationary solution in which there will still be some mixing of some rotation of the particles. This is quite tricky, but also is part of a much more tricky problem for real evolution. You know, Boltzmann equation, I said, is this. Okay. These are the collisions. It's ugly, but it's good. It makes the entropy increase. This is the transport. It's very simple, but it's very bad for relaxation because it conserves the entropy. Okay. If you take this alone, it's not sufficient to drive you to equilibrium if there are inhomogeneities. If you forget about the inhomogeneities and just look at function of t and v, then it's okay, you just have this. It's a real information theoretical problem. But if you put the x dependence and take this into account, then it's a mixture of this, which is mainly information driven, and this, which is more like fluid mechanics driven. And you have to understand the interplay between both, and there it's a very long story about the interplay. For instance, when you look at the evolution of the entropy, say the logarithm of the entropy, if you just have this term, logarithm of the entropy will increase something like this, you know, kind of linearly. But if you add this term, it may very well be that your entropy does something like this. It will can be seen as alternating moments in which collisions are dominating and moments in which transport is dominating. States in which it's more like a hydrodynamical gas and states in which it's more like a homogeneous gas. And it also branches to another big thing in mathematical physics, which is the problem of hypoellipticity, or rather, as I called it in some memoir, hypocoercivity. When you have an operator which is dissipative but degenerates, and coupled with a conservative operator, with some geometric conditions of transversality type between this and there, related to some problems like the ones that Lars Hermander studied for regularity. And so there are these problems which are fascinating, in which you mix problems of degeneracy together with problems of information. One problem on which I worked, for instance, was this one. Take this equation dtf plus v grad xf minus graded v dot grad vf equals Laplace vf plus divergence vfv. It looks like a big issue, but it's just the probability translation of the problem x double dot equals minus grad v of x minus x dot plus square root of 2 times dB over dt. In other words, we are looking at a problem which is subject to a force in a potential W, a friction, and a white noise forcing. Most of the time we forget about this, and we have the usual Fokker-Planck equation, which describes combination of forcing and friction and random forcing. But in real world, the equations are second order, and you have an equation like this, with a diffusive degenerate part here, and a conservative part here, which is non-diffusive. And you have to play on both in order to get the convergence. So I could prove that this, if V satisfies logarithmic Sobolev identity, so let's say if the Hessian of V is bounded below by a positive number, and if the successive powers of V are bounded, derivatives of V are bounded by constants, then there is exponential convergence to equilibrium. And to prove this, exponential convergence to equilibrium, the equilibrium is exponential minus V of x plus V squared over 2 divided by Z. And to prove this, the functional that was used was not the H function. Let's write it like this. But H function plus some combination of Fisher information in which you put various coefficients, like one for the X variable, one for the mixed product, grad XF, grad VF, divided by F d nu, and one for the V product. Actually, it's better to put to first read the V and the. And then you choose carefully A, B, and C. A should be small, B should be smaller, C should be smaller, but B should be bigger than square root of AC with some constant. And by tuning this, then you get the exponential convergence. And this is quite typical of current trends in partial differential equations. When you have degeneracies, things like this, you put the geometry of the problem inside the norm. You adapt the norm to the problem. And if you pick the coefficients here, A, B, C, depending on the coefficients which are in there. So there are all kinds of these tricks in which when it doesn't want to converge as fast as you want, or when the entropy production is degenerate, you kind of adapt to the problem.
Well, thank you very much.
Thank you.